Hello and welcome to Some Assembly Required. In the previous few videos, I hope I managed to impress on you the importance of a good test infrastructure. In our case, this was achieved using Vivado's test bench, a very low code that drives the clock and the two memory files, one for the test program and the other with the expected run state, which I call the test plan. While this system certainly makes things better, it still has a few problems. Those will be the subject of this and the following videos. The first problem I would like to address is this. We cannot be sure that our test plan is correct. I think it is correct, but there's no guarantee that our test program will behave the same way when running on an actual CPU. In order to verify that, allow me to introduce an actual CPU. Ta-da! Let me explain what we have here. We have a CPU, in this case it's the Western Design Center 65CO2S. We have static RAM, in this case 128 kilobyte, but we tie one of the legs low so that it behaves like a 64 kilobyte RAM. And essentially that's it. Just CPU and RAM. Not exactly a complete computer, but pretty close. We also have LEDs showing what the buses are doing. So this is the data bus, this is the address bus, and these LEDs show what the control pins of the CPU input and outputs are doing. Controlling all of this is an Arduino Mega. Now, typically this isn't how an Arduino Mega looks like. This is a compatible version, which is cheaper, but functionally it's the same thing with lots and lots of control pins. I am just going to switch over to this configuration, which allows us to see the LEDs better. The Arduino obviously needs code controlling it. This is the code. It's available on GitHub with links below the like button. We start by defining what pins of the Arduino control which bits of the buses. So the data bus is on these pins of the Arduino, address bus, read-write control, sync bit, that's something that reads the sync pin of the CPU. It's a pin that tells us whether the CPU is starting a new opcode now. Read, modify, write bit, which is actually the memory lock bit. Ready, which is this pin. Vector pull, which is this pin. Bus enable, which we'll talk about in a moment. RAM enable, which is a pin that goes to the RAM module, clock, reset, and CPU power, which doesn't work right now. With those pin mapped, we go into a main loop that connects to the serial, reads a line, and parses it with several commands available. So you can see a list of commands here. To see that in practice, let's look it up. The usual go-to terminal emulator for most systems is called PuTTY. And it can work in our case. However, when working on Linux, I prefer using the same terminal I use for everyday work, which in my case is called console with a K. For that purpose, I have a program called microcom, which simply connects the serial port to the terminal with very little intervention. Let's see how this works. We can ask for help and get a list of commands. First, let's pull the reset line low. With the reset line pulled low, let's give the CPU a few clock cycles. As you can see, nothing actually happens during those clock cycles as the CPU is in reset mode. Of course, once we take it out of reset mode, it will start executing code, and the code execution will soon arrive at the reset vector at FFFC. Of course, since this system has no ROM, what's written at the reset vector is some random junk. If we want this to actually do something, we need to write to memory ourselves. Thankfully, we can do just that. What we just did is write 0300 to the reset vector. We can also read from memory. You're probably wondering how this is possible. Shouldn't the CPU be controlling the bus right now? Remember the bus enable pin I promised you before? What the bus enable pin does is tell the CPU to put all of its outside pins in high impedance mode. This means it doesn't do anything with the buses going to the RAM, and we can control those buses from the Arduino without interfering. In fact, that's what the bus disabled message says. With the reset vector set, we can now write our program to memory. So for example, we can write A9, which means load A immediate, and then say F3, and we can continue execution. So another clock cycle, we read FFFC00, we're reading FFFD03, and the next instruction will begin execution at 0300. Our Arduino code even goes to the trouble of telling us if the sync bit is high, then it decodes the opcode we're on to let us know what it is. And it did load A immediate. As luck would have it, the next command randomly in memory is store A absolute to 38BD. So the next instruction should store to 38BD the value F3, which is the value we loaded into the accumulator here. So that's great. We can change the pins around and see how the CPU is reacting, which is really, really nice, but a bit of a bother. We have to manually enter each byte individually, which takes a lot of work. It would be much better if we could automate this in some way. I think you see where I'm going with this. Aside from the Arduino code, our test harness also has a code labeled host. This is Python code that gives us several interesting tools. Let's begin with the test harness. The test harness is a class. We initialize it by giving it the serial port to which the Arduino is connected, and it allows us control over what goes on. Let's see that in action. With the test harness open, we can now control it. So th reset pulls the reset low. Now we can also write to the memory. So let's write to address 0. Of course, we need to tell it what to write there. And we can see that it translated that into the commands needed to tell the Arduino to write to memory 0 the value C, which is hexadecimal 412. So if we want to set the reset vector, we can just do write memory to FFFC0 and D3 and achieve the same effect. Of course, since this is Python, we can also do more complicated stuff. For example, for address so this allows us more control over what goes on. And by the way, no, I did not speed this up. This is how long it took, which is nicer, but still not very useful. In order to be more useful, let's look at another module. This one is called memfile. What it does is it reads the .mem files we created for Xilinx and parses them so that Python can read the values as well. So if we take the memory image and the test plan that we've written for the Vivado simulation, we can just copy them here. So let's see how that works. We see that we get a printout of the content of the file. The obvious thing is to connect the two together. Iterating the memory file returns a tuple where the first element is the address where the data resides, and the second element is an array of the digits of the byte. So in order to compose that into an actual byte, we need to take datum 1 0 times 16 plus datum 1 1. Doing that will write to the memory the entire test program. Again, I did not speed this up. Now we're in a totally different position. If we pull the reset low, and cycle a few times. Then pull the reset back up. We should start seeing our test program executing. I think you can see where I'm going with this, right? I mean, we have a test plan that tells us what should happen at each cycle. Now, this test plan was written for our simulation, but this is precisely where we can put our code to the test. See whether the test plan written for our simulation runs properly on our CPU. So that's obviously the next step. Read the memory file, write it to the memory, read the test plan, and parse and execute it. And seeing where this fails is pretty instructive, telling us where our CPU, written according to our best understanding of how a real 6502 behaves, differs from a real 6502. Let's put that to the test. Run test needs the serial port where the Arduino is connected, and it needs the memory file and the test plan file. Let's see how we do. We're failing fairly early. Verification failed on line 22, bus access for wrong address. So line 22, we expect a read from the reset vector. So obviously we're having some mismatches around the beginning of the test plan. Some of the reset response timing were off. I'm skipping a detailed review of what was wrong because I think it's less relevant. Just assume that I fixed the test plan to make the reset cycle pass the real CPU. Now, if you're wondering, yes, I'm changing the test plan to accommodate the real CPU, but when I'm done, I can take this test plan back to our simulated CPU and says, this runs on a real CPU, let's adapt the virtual CPU to accommodate that. And we got further. We got to line 83. Line 83 says we were expecting to read from address 300 on the last cycle of the command, and instead we read from 3C4. It seems strange, but actually we have this comment here, which we wrote in the past, which kind of makes it okay. It says invalid address access legacy 6502. To understand what that means, let's go back to the datasheet for the 6502 and go to the caveats section. The very first caveat is index addressing across page boundary. Let's see. Our opcode was read from 3C2. So let's search for 3C2 in the memory file. And it says branch equal to address 400. Here's what you'll note. 400 is on a different page. The most significant byte of the address is different than the one from which we're jumping. When that happens, that's program counter relative. Footnote number 1 comes into effect. It says page boundary, add 1 cycle if page boundary is crossed when forming address. The program counter starts at 3C4, which is the next address after the branch equal. We add to it 3C. We wind up in a different page than the one we started at. So we need another cycle to add 1 to the most significant byte. That's what this comment says. What this comment says is that there is a fundamental difference between what the original MOS 6502 did and what the Western Design Center 65C02 does. The original 6502 during this cycle would access an invalid address. This invalid address would compose of the least significant byte belonging to the correct address we're supposed to jump to, and the most significant byte belonging to the page we're jumping from. So it was this composition of two valid addresses into a completely random result. If you look here, that is exactly what we have. We're supposed to jump to address 400, and we assume we're reading from 300. That's what our CPU is implementing. All we need to do in order to make this test pass on the 65C02 is change that to what the 65C02. What the 65C02 says, extra read of last instruction byte. Effectively, it would read 3C4 because that's what the program counter is pointing to until the calculation is done. So 3C4. And indeed, that's what we see here that we got in practice. Let's run the test again. Line 85, same comment, same problem. We can change that to 404. In fact, let's right now change this to C6 and this to 408. Line 148, 8 to C, branch A, same problem. So 8 to E. Notice that so far we're doing pretty well. We passed 163 of our tests. So we're not doing particularly badly. Let's see what 163 is. 163 is we're expecting to write 20, and instead we are writing 60. Let's see what that means, because this is actually important. 4 means bus access verification. So we're doing just a generic bus access. Before that, we see EA is no operation at address 831. So that's the last instruction we're executing. 831. No operation. And right before that, CLI, clear interrupt. So what we have here is this. We're setting the IRQ line low. So we're asserting an IRQ. Next, we're running several no operations to make sure that the IRQ doesn't trigger. We expect to have the IRQs masked. And this is what this test is verifying. Then we're clearing the IRQ mask. We expect to execute one instruction after that. And then we expect to start having bus accesses that are the execution of the IRQ. So we're doing dummy reads from 832, and then we're starting to write into the stack the state before going into the interrupt vector, that's FFFE and FFFF, and then going into the interrupt routine. So that's the test plan. And it went wrong on this line. We were at 0832 and we wrote 0832. And the next thing we wrote is the flags register, which means that the flags register contained a different value than the one we were expecting, which is really not good. It means that some instruction here was supposed to change a flag, and it did so differently in our simulation than it did on a real CPU. That's an actual bug in our CPU that we caught here, which is exactly why we did this exercise to begin with. So obviously, if 60 is what a real CPU is writing, 60 is what should be here. This is the reference. This is what is by definition correct. This time, unlike the branch example, we have no excuse. We have no caveats we can fall back to. This is an actual bug. Let's run again. And this time we run to completion. everything passes, including the instructions we wrote in the last video. It's pretty close to the real thing, just not 100%. One thing to say about the mismatch problem, I'm not 100% sure what the state of the flag is on startup. I believe one of the instructions along the way should have said it, but I'm not sure. The missing flag is the overflow flag, and it would be better to include a clear overflow at the beginning of the program to make sure we start at a known state. However, I cannot add an opcode at the beginning. It would shift everything, and it's just too much work to do. So that's what we're going to be addressing in the next video. We'll try to have making changes to the test program easier. In the meanwhile, thank you for watching.